We're going to zip through this, so let's see how well we do. You may also like to draw for yourself a tan curve. We're eventually going to draw all of them, but this will be the first one. And you may notice I have all this extra space over here on the right-hand side of my graph, and that's on purpose. So you probably want to make your plane the width of your page, but don't use the whole width. Just have some space extra left over. Okay. So, you might want to get a friend to help you with that. You might have more success. Hey Ivy, it's nice to see you too. General solution is just a way of writing your answers. That's it, full stop, okay? So remember, so far we've been looking at T results, right? And auxiliary angle. I don't know if you're getting sick to death of me telling you what these are, and what they're about, and how they relate to this. When I remember going through 3 unit, I sort of got these as different things, and I sort of understood by the time the exam came around how to do each one, but I didn't understand any of their relationships with each other. So I don't know if that means I was poorly taught or I was just asleep at the time, but I'm saying it like 5 to 10 times just so that eventually one of them will sink in. So these 2 methods are about changing the way a problem is written so you can solve it, right? Turning it into something we're already familiar with. This has nothing to do, despite the name, with actually solving questions. It's just about how do you write out and express, articulate the answer you do get after you've done T results or auxiliary angle or like a simpler type of question which you don't need to rephrase in that way. Okay? So to draw out the way it works, let's consider just a nice simple equation like tan x is equal to 1. Okay? Tan x is equal to 1. Now, ordinarily, we would get supplied a domain with this kind of question. For instance, because you guys voted for radians, 0 to 2 pi. That's pretty standard, okay? Now, tell me again, remind me, why is it that we treat equations like this, you have to get supplied with a domain? Why is that?
Because they have many solutions.
Okay, good. There are many solutions to this equation, not just many. There's an infinite number, right? Which is different to say quadratics or cubics or other kind of polynomials you've got. There might be many solutions, but there's still a finite number, okay? The problem here is if you don't restrict the domain in some way and say, I just want these specific solutions, you're going to be writing them forever, okay? So that's why I've got over here, this is 0 to 2 pi. Okay, so I've got pi in there, 2 pi here, and I've got 2 asymptotes. Alright, so that's what we're used to, right? Now, tan x is equal to 1. I've drawn my graph in there, just so that we can illustrate this visually as well as algebraically, okay? What kind of solutions am I expecting? Well, something like this. That's very straight. If I draw in the line y equals 1, okay? In this domain that we've chosen, I'm expecting 2 solutions, right? Namely here and here, okay? Now we're pretty good with our exact values, at least for simple ones like this. What angle are we expecting for the first solution? Pi 4, thank you. And you know, I've sort of drawn, you trolls, I've sort of drawn my graph well enough. So there's pi 2, that's about half, okay? So, one of them is pi on 4, okay? And the next solution is pi radians that way, right? Namely, 5 pi on 4. Okay? So we would say, there's our solution in this restricted domain, okay? But the fact that we've got these 2 solutions actually means because trig graphs are so repetitive, we call them periodic, right? So they've got a period and they repeat again and again and again. We can actually take advantage of this to not just write these 2 solutions, but all the solutions, or at least some of them, until we can see a pattern, right? So if I extend my graph a little bit, including this this y equals 1 line, let's take it all the way over here, and let's see how much space I'll have graphs, I'll be able to go on. Okay? So let's see here. So Okay, so I've got at least enough space for another 2 copies of the graph. Okay, so it looks to me like I'm heading all the way up to 4 pi. That's 3 pi. Okay, so I can see another 2 solutions, right? Pi and 4, 5 pi and 4. Next one will be 9 pi and 4. We're on the ball today. We're good at fractions. I can add fractions. The last one. Yeah. Yeah, it's a shame. It's lucky for you I've already written your report. Okay, so there's my 4 answers. Okay, pi and 4, 5 pi and 4, 9 and 13. Okay, so let's just list these out here. What I'm going to do is for this next part of the answer, I'm going to ditch this restriction. Okay, so I'm going to say pi and 4, 5 pi and 4, 9, 13, and so on. I could keep going. And this domain is, well, I'm looking at all of them, really. Okay? If I want to be really correct, I also ought to have not just 3 dots at the end, but 3 dots at the beginning, because they also go in an info direction that way. Okay? So, all of these solutions, right, because they're so orderly, right, I should be able to get some kind of expression that puts all of these together, right, rather than listing them all out. Okay? So what do these all have in common? Well, to get from one solution to the next one, because of the shape of tan and the way its period works, right? I could really write this as pi and 4, right? Then my next one is pi and 4 plus pi. I added that because that's the period, right? And the next one is pi and 4 plus 2 pi. And so on, right? Okay? So what's a better way to write this than actually to write out every single option? Well, I can sort of get it, generalize, and say, look, here's an expression which will cover all of them. Okay? It looks like every single one has pi and 4 in it, right? That's kind of like your related angle, right? So I'm going to have a pi and 4. And then what do I add on? Well, 0 lots of pi, 1 lot of pi, 2 lots of pi, just integer bunches of pi, right? So to sort of summarize them together, let's call it n pi, where, and you have to specify this by the way, where n is an integer. Now, this is where all of those hours laboring over set notation and like, why are we learning this, okay, are going to be worth it, because you have to write this so many times that to write where n is an integer is going to be whole hours of your life that you'll never get back. So instead, use set notation. Okay, that's a faster way to write than saying n is an integer. Where n is z. That's, yeah. Okay, so what's your question?
There's so little difference.
You'd be surprised. You're going to be writing this a lot. Sometimes you're going to write it multiple times per question. But anyway. Okay, so, yeah, question.
You write it fancy like that?
No, but you don't have to write it fancy, but you do have to introduce this letter. If you're going to talk about it, right? You have to it can't just pop up out of nowhere, a wild N appeared, okay? And you also have to not just introduce it, but you've got to qualify it, right? You've got to say it's an integer. So most of you will find you'll start writing this, and the textbooks write it like that as well. So you sort of might as well get used to it, okay? All right, any questions before I move on?
I'll just write like Z type. Is that allowed?
No, because Z, right? That funky looking Z is actually the name for a whole set, right? So it's not, it's the set of, 0, 1, 2, 3. Actually, it goes the other way to -1, -2, and so on. So it wouldn't make sense to put the Z here because I want this to be a number. I want it to be 1 or 2 or 3 or 4. I don't want it to be every single one all at the same time. Okay? All right, so this is what we call, this is the general solution, okay, for this equation that we started with. Okay?
From here? Sorry.
Okay, is that all right? So before we leave off this example, and I wonder if you can see why I picked out tan first, okay? Let's just consider some different result. Say tan x is equal to 2, okay? So just keep it simple, okay? Tan x is equal to 2. Now this is not an exact value, right? And if I draw in my my y equals to 2 line, okay? You can see I'm still gonna get the same solutions, right? It's just that the amount that they're moved over, which here we call pi on 4, right? The amount they moved over is all just a little extra. Can you see that? They're all shifted a bit further. So it's still going to be in this form. It's still going to be something plus n pi, right? Something plus n pi where n's an integer. So to work out the something, get your calculator out. And we're in radians, right? So make sure you're in the right mode, which I am not. And because tan x equal to 2, right? Where did we get this pi on 4 from before? It was the angle that satisfies this equation, the first one. Okay? So the same way, you're going to do tan inverse of 2, right? That'll give you the angle that satisfies that, which I think I heard it was 1 point. Let's do it to 2 decimal places is fine. So it's 1.11. Okay? So one of the other benefits of doing it in radians, you don't have to put units on there because we assume it. So I suppose I should put approximate. Okay. So it's going to be that angle. That's our substitute for pi on 4. Okay. Plus your n pi, and every time you're going to get a new solution. Every time you increment up, 1 pi, 2 pi, 3 pi, 4 pi, and it works for negative values of n as well. Because if I drew backwards, okay, you'd keep on going pi radians each time. Okay. All right. Now I just introduced it for tan. What I want you to have a think about for the next 5 minutes is, this is what the general solution for tan looks like. What would it look like? I'm doing this in a very specific order. What would it look like for cos? I'll give you a clue, okay? Or not so much a clue as a tip. We developed the general solution, okay, by graphing it out and seeing how it worked. That each time you just move forward pi, okay? Now with cosine, it's not the same. With sine, it's not the same either, okay? They're all different. My tip is to draw it first, solve it for something simple. Like we picked tan x equals 1. I picked it because it gave you nice angles. Pick something else, okay? Something nice and not too complicated so you can focus on how it works rather than the individual numbers. See if you can come up with a general solution for cosine. I'll give you about 5 minutes to have a think about it.